Hello everyone, my name is Zaved Iqubal Ahmed. I work as an assistant professor in the Department of Computer Science, Pandit Deendayal Upadhyaya Adarsha Mahabidyalaya, Dalgaon. And today I'll be discussing about quicksort. This is the outline of my presentation. It has introduction, the sorting problem, different sorting algorithms, quicksort algorithm, and conclusion. Well, before going into quicksort, let us briefly discuss what is sorting. Well, sorting is arranging data in a particular order. And a systematic step-by-step way to do the arrangement is called the sorting algorithm. Now, we can do the arrangement of data in different ways. We can do it in ascending or descending order in case of numbers, or in lexicographical order in case of words or alphabets. Now, let's discuss why do we need sorting. We need sorting because by keeping the data sorted, we drastically reduce the sorting time. Like in real life scenario, let us consider a telephone directory or dictionary where all the information are kept in a sorted order, and we can look for a keyword very easily in them. So this is where sorting is very useful. Now the sorting problem, if we see what it is, actually we'll try to understand with this example where we are looking here. What we have is a group of people of different height, and we want to arrange them according to their height, and this is in ascending order, let us say. So now the sorting algorithm, actually the sorting problem, is looking for a systematic step by which we can actually arrive at this arrangement. So this is our sorting problem. Okay, moving forward, we'll now discuss about sorting algorithms. Now, sorting algorithms play a very important role in computer systems, and there are many sorting algorithms such as bubble sort, insertion sort, selection sort, quick sort, merge sort, and so on. And each algorithm follows different paradigm. In this presentation, we'll be discussing about quicksort. Now, quicksort, it is a very elegant and efficient sorting algorithm. Tony Hoare invented it, and it uses a divide and conquer paradigm. The basic idea behind quicksort algorithm is that while sorting, let it be in ascending order, a number n is considered to be in its sorted position if every number before n is less than n and every number after n is greater than or equal to n. Okay, so it actually considers that n need not be sorted, or it is already sorted, if all other numbers before n are less than n and all numbers greater than n are actually to the right of n. So let us try to understand this pictorially. Now, in this group of people, if we consider the first person and try to check whether he is in the sorted position, we can see that there is a person to its right who is shorter than him. So therefore, we can say that this person is not in its sorted position, because to its right, all of them should have height greater than him. Likewise, the next person, he has all other person to his right taller than him, but there is one person to his left who is taller than him. So therefore, this person is also not in its sorted position. Likewise, in every situation, we can see that none of the person are in their sorted position. But in this example, if you see, this person has every other person shorter than him to its left, and all other person that are taller than him are to its right. Therefore, this person is in its sorted position, and this person need not change its place while sorting. So this is the basic idea behind the quicksort algorithm. The heart of the quicksort algorithm is the partition process. In this process, an element is selected as a pivot, and based on the idea discussed in the previous slides, the pivot is placed in a sorted position. But how? Let's take an example. In this example, we consider a list of numbers and they are not sorted, and we want to sort them in ascending order. So first we have to run the partition process. So in that we first consider the pivot, and the pivot is selected as 5. Now there are various mechanisms to select pivot, but in this case we are only considering the first element as pivot. Okay. After that we assign two markers I and j that points to 6 and 9. After that we put a condition saying that we will advance I to the right until it encounters a value at a position that is actually less than the pivot. So it will do it until we have any number less than the pivot. It will go on moving the I, the marker I. But the moment it encounters any number that is greater than the pivot, it will stop there. So in this case, I has an element 6. So therefore it's already greater than 5. So we're not going to move I. So after that, we go to J. Now it is said that we will advance J until we find a number that is actually less than pivot. So we will advance it whenever we find a greater element. So J, that's pointing to 9 and it's greater than 5. So we move it towards left. Now again 8 is greater than 5. We'll move it towards left. Now if you see, J comes to a place where this 3 is actually less than 5, and therefore the condition holds, and we can find that I and j both they hold. Now when I and j both hold, we are going to do one thing, that is we are going to exchange the value at I and j, that is 3 will go in the place of 6 and 6 will come in place of 3. Okay. After that again we go to the first rule and we try to advance I to the right. Now the condition was that I, if it has value less than the pivot, then we will move it to the right. So yes, it has something less than the pivot, it will go to the right. Now 2, yes, it is less than pivot. 1, it is less than pivot, and we come to 12. Now it will stop because I is pointing to a value that is greater than 5. Now we can come to the next condition where we have to move j if it has a value greater than 5. Yes, it has value greater than 5. So it moves to 12, which is also greater than 5, and it comes to 1. Now when it comes to 1, we can see that j has already crossed I. And when j has crossed I, what we are going to do is we are simply going to swap the value at position j with the pivot. That is 1 goes to 5 and 5 goes to the position of j. So by this mechanism or this process, what we have done is we have brought the value at a pivot in its sorted position. This is the partition process. By this we have actually put 5 in its correct position. Now we can see that after having 5 in its sorted position, that means now 5 need not be sorted again. It has fixed its position. So now the whole problem divides into two sub-problems. And in these two sub-problems, we are again going to use the partition process similarly. Now, if we take the sub-problem to the left, we'll again select a pivot 1 and try to put it in its sorted position. Yes, we could put it. Then again, we select a pivot that is 3 and try to put it in its sorted position. Yes, we could put it. Then we come to 2 and 2 is in its sorted position. We then come to 12. Well, 12, yes, it goes to its sorted position. We select 9, put it in its sorted position. Select 8, put it in its sorted position. And now 6, when all other elements are in their sorted position, we can consider that 6 is already in its sorted position because it has no other place to go, because all other elements have actually taken their place. So therefore we need not sort 6 and simply terminate the process. In this way, we have used quicksort to sort the list of numbers that we have considered. This is the quicksort algorithm, where we can see that it recursively calls the quicksort. So this is a recursive algorithm where first it runs the partition process, then it runs the quicksort algorithm on the two sub problems that we have seen earlier. That after finding the position of the pivot, we get two sub problems, and these two sub problems are further actually put into the quicksort process. Now this is the partition algorithm that we have used. Quicksort has a wide application in the field of computer science and engineering. The quicksort is indeed a very efficient sorting algorithm, and it can save a lot of time in sorting large data. In the best case, it has time complexity of big O n log n. However, in the worst case, it has a time complexity of big O n squared. That is, this scenario, the worst case occurs when all the elements are given in sorted order as input. Okay. With this, I'd like to conclude my presentation. These are the references that I've used while preparing this presentation. Thank you.